think that should do it.
Fantastic. Can I start?
Yeah, let's go ahead.
Fantastic. All right, so we are on the fourth exam review of the spring 2025 semester. It's 3 o'clock, so we'll go ahead and get started. So as usual, I'm just going to start off with something that did go out in the announcements. I think it either went out like the past 24 hours, so recent. So if any of y'all are starting to feel that like hectic feeling of the semester is almost over, but it feels like there's a whole bunch of stuff left to do before we get to the end, that is how a semester at UT Dallas works, and that is especially how spring semesters usually feel. So you have my apologies for that, aside from we're all in it together. So Exam 4 is this Saturday. That is May the 3rd. It is still at 10 o'clock in the morning. I will pull up those seating arrangements if you'd like. They are the same as we've seen before. Whoopsies. And I've been preparing for other classes because I've also been trying to figure out what all left is due. Don't forget, by the way, the end of semester survey. Do that. Don't forget to do that. And somewhere through all these announcements is a lovely little table that should give me room assignment. Oh, no, the updated room assignments went somewhere else. So we are all full of what do we have left to do and where is it going and what are we doing? But there it is. So room assignments. So these now are the room assignments that y'all have had for exam 2 and exam 3. We did have a little switch where we were somewhere where one room was different on exam 1, but we are exam 1 was so far away from where we are now. So these are the room assignments. We should also be using those for the final. We'll be double checking that soon, but you guys can take a look at those. So wherever you were before, we're there again. So general things, chapter 15. So this does say section 15.3, 15.4, and 15.5. But something that I'm going to mention that you still need, which was in especially 15.2, was dealing with entropy. So we do expect y'all to still have that conceptual information about entropy. So while you'll find questions specifically on these various pieces, keep in mind that it's really all of chapter 15. There's really not that much that we've taken out and removed because the hard thing is that especially for assessing if a total reaction has a positive entropy value or a negative entropy value, those are things that you actually do still need. So there's some stuff in there still. Chapter 16, which is just 16.4. So this was all the stuff that related especially delta G to Q, or the standard delta G to K. So there was a little bit of information in there connecting all of those pieces together. So that's what's in 16.4. A lot of times as we go through the units, it can often seem like it was just part of chapter 15 all along. So our rearrangement hopefully felt relatively natural. And then chapter 19, it's basically all of it. There's a couple of things we don't specifically test on, like concentration cells, batteries, and corrosion. So there's especially terminology in there that we simply won't use. And I've got this note in here that since we expect you to remember conceptual ideas about entropy, end of chapter questions are just the recommended ones posted for 15, 16.4, and 19. 16.4 is already separated out. So as you guys get in there to look at all of those, that's going to be my recommendation for end of chapter problems. So nothing, no specific list this time. So really just 15, the 16.4 that's already separated, and chapter 19. Relatively straightforward, all of those things. So that really gets us through those bits of introductory stuff. I know we're still going to wait a little while for more questions to come in. So I went ahead and asked my class what questions did they have. And so I'm actually going to start answering some of these, especially because some of these actually were about the final. So as we get towards the end of the semester, I had 4 questions that were actually about the final. So this one says, will the final focus more on basically which exams out of the 4? So this one is really difficult for me to answer because there's 2 different answers to this question. One is if you actually went through and were like, well, how many questions? How many questions are on each one of these chapters? Like an actual numerical number. But there's a second answer to this question, which is what it feels like. So this is always my personal conundrum, which is if we looked at some of the exams you've already taken, and I just asked you at the start, so how many of these required calculations and how many were conceptual questions, and you had to guess. Usually what you tell me is usually more based on how long it took you, not actually the number out of the total that there were, but out of the total amount of time, how much time did you spend on the conceptual versus the calculation questions? And that's the same problem I have with this question because first of all, we haven't written the final yet, so I don't really have this answer. But the other part of this is you're going to have, even if I had the answer, you're going to have a way that it feels. So since exam 1 was so very far away and we have not dealt with molality or weight percent, we haven't done freezing point depression. We haven't talked about vapor pressure since exam 1, really. Kinetics, exam 1. So those questions tend to like stand out in your memory more because they are basically because they're ones that we haven't been talking about as much over the semester. They have a tendency to stand out in your mind a little bit more and feel like they're a bigger emphasis than maybe they actually were. In comparison, 2 and 3 go together really beautifully. And because of that, 2 and 3 both tell a really nice story together because this is basically where equilibrium is. Equilibrium, acids, bases, and that little bit of solubility. So it's probably going to feel like 2 and 3 are there the most, but that's also because equilibria, acids and bases, and then tacking a little bit of solubility covers both of those exams. So I don't have a really great answer for that because I don't have that. But so that's always been a difficult question for me to answer. I respect it, which is why I wanted to try to answer it, even though I did a pretty bad job of answering that question. But did want to respect the feels. Are we going to get tell me tested on the final exam 4 stuff since we have just 1 week until the exam? Did I actually grab a calendar to actually show you guys what this looks like? Did Dr. Diekman leave his lovely schedule-y thing? So basically what I'm looking for is something that will actually show you guys how long we actually have until the final, because it's a pretty quick turnaround. It is pretty fast. But it's a week and a couple of days. So I'm going to grab this and show you guys what this looks like. So the 2 yellows on here. So here is our lovely, so I can write with. So here is exam 4, and it's on Saturday, May 3rd. And then here is the final, which is Tuesday, May 13th. So I will actually say the other thing with the final is that I don't know if you guys can notice, but there's this lovely week here, and it says things like there's a nuclear homework, which is true, and we are covering nuclear. this week. So the final exam is the same material as exams 1 through 4 plus nuclear, plus whatever nuclear content we get through. So plus nuclear, write that one on there. Because there is at least 1 or 2 nuclear questions. Even though I think there's like 36 questions, it's a 90-minute final. So I'm just gonna put this 90-minute final. We do tell the registrar's office to give us the rooms for 2 hours and 45 minutes. That is for, based on some past experiences, it works better for the team. If you're curious about that, then you can talk to me about what that means. But it is you get 90 minutes for the final. 90-minute final. 90-minute final. Still 80 minutes for the individual exams. Final exam layout. So the one thing I will tell you, because this is true, the final is all multiple choice. There's no short answer on the final. So y'all don't have to worry about short answer on the final. We don't have to worry about grading it on the final. None of that. So final exam is all multiple choice. That's all you have to worry about for the final. I think it's 36 questions. I'm going to put a little question mark by that. But I think it's 36 questions for the final exam. This one says, will there be an overall curve at the end of the course? So we post our actual grade breaks. So in the syllabus, always makes me laugh. It's like, oh, we're going to the syllabus. In the syllabus, one of the things that we actually have, and it's posted in the syllabus, if you guys didn't catch me doing it, I did in fact just go to the syllabus and nab this. But what you might notice when we look at the grade breaks that we use that's posted in the syllabus are things like an A minus starts at an 89. A B minus starts at a 78. And that really is technically like an 88.5 rounds to an 89. So again, we can get that a little bit more granular. A 65 is a C minus. So when you say, are we expecting the course to be curved? These are the grade breaks. That being said, because these are the grade breaks and there's already a bit of generosity put in here, because we could have used 90 and above is an 80 to the 89 is a B, a 70 is a C minus. We could have used those, but this already has some amount of give added into it. So we are usually not nicer than this. That being said, we do look at all of the final grades at the very end of the course to see how everybody did. But usually, since we have adjusted exams as we've gone through, we had an adjustment on exam 3. Usually by the time we add an Alex in participation in, you guys don't typically need an adjustment to the final course grades aside from this. So what's in the syllabus is typically what we use. And that's that. Sorry. I will show you why I'm smiling. If I can just make these bigger. Oh, I got stuff in the way. That's fine. I'll move it in a minute. If we decide to cram, what would you consider to be the most high yield topic to focus on? So I gotta fess up, for this exam, I really don't know. And that's unfortunate because I definitely understand the idea. One of the things, honestly, if I was trying to figure out like, oh no, I'm running out of time, how can I make the most yields out of my time? Honestly, what I would do is I would look at all of the equations and I would make certain that I at least knew how to get things from these. Because and actually one of the things I would say, because you can kind of see how often it comes up. Here's E standard of the cell. Here's E cell. Here's E standard of the cell. There's E standard. I guess I should get rid of the one that wasn't standard. Make that go away. And here's E standard. Some deals about delta G standards. That's in there a fair amount too. Look at these guys. So I would basically focus on some of these calculations and see what I could get out of those. That being said, I have to admit, if there was any, if I only had to pick one, and I don't like this game at all. I frankly would be worried about how to make sure you could get E-cell standards, because honestly, if knowing how to calculate E-cell standard is not something you currently know how to do, that is going to be a problem. In part because of how many other times it shows up, but also the concept behind how do you know if a reaction can go or not, if you're told it's a galvanic cell, what are some assumptions you get to make, things like that. Those are all things that you need. So know that those joining live are just now in because I messed up the link. So I am really sorry about that. The good news is we've mostly been talking about miscellaneous things and in general information about the exam, and that part will be recorded. Honestly, the vast majority of it was already sent out through announcements. And frankly, if you got this, you probably are one of the people who check all the announcements. So while I know that that's annoying to have missed that beginning portion for those of you joining in live, I'm going to take an assumption that the majority of y'all have been reading the announcements, and that's how you managed to get in here. Overall curve at the end of the course. So the short answer is check the syllabus. Because there basically are more generous grade breaks than what you might be expecting, and that's where we start. We did talk about deciding to cram. This one's a really difficult question, but we'll go ahead and go with E-cell standards. And then this one's, what's the best way to memorize redox concepts, drawing mnemonics, a table, something to write down before my test and refer back to. So this one is one where for oxidation versus reduction, I usually use oil rig, which this one is for oxidation is loss of electrons, reduction is gain of electrons. And then the other thing that is helpful for redox concepts, personally, I don't think about this as a particular mnemonic, but when you're looking at this giant table, which I know as I blow this up is still not going to look fantastic, one of the things to keep in mind is that y'all already know about fluorine being the most electronegative. Most electronegative. So when you think about this table, the fact that the top is most easily reduced is part of this table. So keeping in mind that that this table will be given to you as part of the potentially useful information. And so that idea of your fluorines at the very top, it's the most electronegative, it wants electrons the most, it's the most easily reduced. And then on the bottom, we have lithium. And so lithium being one of those alkali metals is going to be most easily oxidized. And I understand that when you look at this, you're like, oh, but is lithium really the best one to be most easily oxidized? There's a couple of other alkali metals. We could have a conversation about, are some of the other ones actually better? In this case, we're just looking at how to orient ourselves on the table, and keep in mind that the numbers in the table are from data actually collected. So while it's been a long time since we talked about periodic trends and some of the exceptions you sometimes find in periodic trends, this table is all based on real world data. So that's part of the other reason why we just give you the table instead of using a periodic table and say, tell me and guess. We want you all to just use the actual real numbers that we have established from experiments. So yeah, I don't have a great mnemonic for redox. I have to admit, honestly, I am one of the worst people to ask about mnemonics. I respect that it can sometimes be helpful, but I sincerely am one of the worst people to ask about mnemonics. I usually got frustrated and just brute force memorize things. End of chapter problems are recommended. I don't have a separate list for concepts versus calculations on here. So I'm just going to say, just see the recommended problems. I realize that you probably want a more specific list of which ones would be better than others. I honestly don't have that ready to go. You guys can read through the recommended problems and see if there's some that seem to be more calculation focused than others in there. And then what are some other methods rather than into chapter problem study for the exams? So this is one of those things where keep in mind you guys still have Alex. And I would tell you to understand Alex. What's going on in there. I understand that since they have deadlines, a lot of times people are just like, I'm just going to get through Alex and not worry about what's actually happening. I get it, but that is a problem. You guys also have that 2024 exam to give you guys a general idea of things. And the thing I like the most about the 2024 exam is that the questions are in a random order. So one of the things that is the most difficult to practice is how do you look at a question and figure out what to do? And the fact that the 2024 exam from last spring is in a random order is one of the things that can help you with that. The questions aren't labeled, none of that. So that might also be helpful. And then we all have workshops. So Dr. Bacone, Dr. Diekman, and I all have workshops. So you might chat with people either from your lab, other people you know, and see if you can get all of the workshops for practice in there. So I don't think that advice is super different from things we've talked about before. SI sessions are still a thing. Those are still going on. The SIs make new content every week that can certainly be helpful as well. Okay, so now that we have some people in there and I've also vamped a little bit, do we have questions from the chat?
None have hopped up so far.
Okay, no worries, no worries. So most of the questions that I got asked from my class have to do with electrochemistry. So that was the thing that I got asked about the most. But let's go ahead and take a look at some of these. If you guys have other questions, you can certainly drop those into the chat. So this one says, how do we know when we're in basic conditions, which side the water and the hydroxide go to, since they both have oxygens and hydrogens that can help balance the equation? So this is one of those where there might be a better answer to this question. But for me, when it comes to balancing, I usually think about this as a procedure, as in a follow the procedure, because the difficult thing is sometimes you have, I'll just give you some examples. So sometimes you might have something where you are dealing with something that has, sorry, I'm looking for an example off of my thing. There we go. MnO4 minus 2. So I'm just gonna look at a half reaction for right now. MnO2. Sorry, MnO2. MnO2. So part of this idea of like, how do you know where things go? You can play the game a little bit and say, okay, if this is my half reaction, then I know that whichever side doesn't have enough oxygens is going to be the one that winds up with the hydroxides in the end. So whichever side that I begin putting my waters on, this is the side that will also in the end have the hydroxide. But the problem is that that doesn't necessarily guarantee you that it's the product side, that it's the reactant side. It doesn't guarantee you that it's the reduction reaction, that it's the oxidation reaction. Because the whole idea of adding waters and then continuing to balance the reaction is all about balancing the elements. So to finish this one out, so I balanced my manganese, I do only have 1 and 1, and then here's my oxygen with 4 here and 2, and now 2 more, so that's 4. But now I have these hydrogens, so now I have to go ahead and add 4 hydrogens. But if we're balancing in base, this is the part then where I have to fix this because I can't leave it in acidic conditions like this. But everything is also balanced right now. So I will go ahead and add my 4 hydroxides to both sides. So since now I have hydroxides added to both sides, this side now becomes 4 waters. And now I have a bunch of stuff written down. So now I'm going to go ahead and take a moment to rewrite this. So I have 4 waters plus that manganese ion goes to another manganese option plus 2 waters plus the 4 hydroxides. Now I have extra waters, so now I need to get rid of those. So I get rid of that, and I just get a 2 right there. I am also going to go ahead and think about my electrons. So my oxygen, there's 4 of them. It's got a -2 oxidation state for a grand total of -8. Is equal to -1. That's a +7 for that manganese. This oxygen's also -2, a contribution total of 4, has to be neutrals. There's no charge here. So this has to be +4. And then so for my electrons to balance out, I should in fact then need to add 3 electrons to this side of the reaction, which is the same answer we would have gotten if you decided to balance this by the charge. So I also could have balanced this by taking this negative charge here and these 4 negative charges here and asking, how do I balance my charges out? And I could have added my 3 electrons that way. So you basically should wind up with wherever you begin to put the waters is likely where you're going to wind up with the hydroxide and not the waters in the end. But again, that in this case happened to be the product side. It doesn't have to be the product side because I just went ahead and grabbed this off of the standard reduction potential table to give a quick example. Also, that way I could double check my own work to make sure that I've got everything set up correctly, and luckily it agrees. So if I had swapped my 2 reactions if I had swapped my reactants and products when I started, I'd have a different answer. So there's no particular way of knowing which one goes first on here. So this to me is more of a procedural, but you can say that wherever I start, but with adding waters, if I have hydroxides in the end, is where I'll have hydroxides by the end of it. And again, as far as basic or acidic conditions, we tell you. So we basically will say, hey, balance this in acid, or hey, balance this in base, is how that one works. Okay, next up, how does a galvanic cell work with nonmetals needing a surface site? So something that you might have seen, looks something like this. I'm just going to try to make sure that I grab an actual galvanic cell. That'll work. So I'm going to go ahead and show that. Yeah. Nope. Hold on. Brain is braining. Copper. Yep. That's not what I wanted. Copper plus 1 molar, aqueous, comma, copper 2 plus, aqueous, 1 molar, salt bridge. Also, I should have put platinum over there. Well, actually, yeah. And that is being oxidized. So now I need something that's being reduced. Just make this something like gold's. Gold's always up for being reduced. Aqueous, 1 molar. Also, I realize that it's difficult to see what I have in my hand. It is the potentially useful information page that's available in the 701 section. So in case you're curious as to what I'm holding in my hand, I have a physical copy because I printed it out because I wanted a physical copy. And now this is too big, so we're going to shrink this a little bit so I can actually see it all on one page. So the idea is, so the question's asking about how do I get non-metals? And I didn't use any non-metals, I only used metals. But I think the thing is that this also applies for things like chlorine gas, works for iodine, works for bromine, works for all of those in here. But what you might notice is that I have this thing that's not part of the reaction. So there's different ways for that to work. So in this particular case, because everything I have is aqueous, we can essentially have a piece of platinum wire. Nope, that did not erase. Erases when I do that in the classroom. So basically this is a platinum solid. So this is basically like a little platinum wire that hangs down. And basically what happens is you have copper ions, copper 1 ions that basically pick up or drop off, I should say, that basically interact with this wire and give their electrons as they touch and as they interact with the wire. So there is an idea of chemistry that's happening in different phases. So you have a solid wire that is interacting with the aqueous species. Even though the platinum's not actually doing any chemistry, the platinum's just sitting there. But the platinum is useful for carrying electrons. The setup gets a little bit more sophisticated if we're talking about dealing with gases. So if we're dealing with gases, let me finish my little drawing of this guy. Here's a beaker. Here's the liquid. Everything's in liquid. There's a little wire, all that jazz. If we're talking about a platinum wire dealing with gases, what usually happens is you have still your platinum wire, so that's still there. But now things are a little bit stranger because for one, usually then if you have to have a gas in here, there's usually some sort of glass tubing that comes down, and I'm going to kind of fake this a little bit because we still need some of this to interact with a wire, but you have glass casing around in here so that you can have, if you, for example, wanted your chlorine gas to be in here, so there's some sort of tubing attached. And then down at the bottom, you're going to have some form of membrane that can actually still interact with the liquid and solvent itself. And sometimes you've got a little bit of that going on. So there are ways to get your nonmetals to interact with the overall reaction. But in general, this is something that we consider to be more of a game of engineering. So exactly how this thing works, we don't typically test on that. The fact that you have to have the platinum there and that the platinum doesn't interact with the reaction itself, aside from a physical site for the reaction to take place, that we will ask. So in the case of my platinum dealing with my copper, because this is my oxidation reaction, my platinum is my actual anode. That anode is the site of oxidation. And this is the part where calling something the site or the location becomes an important piece. So we're not just saying that that is a thing that is taking place in the reaction, but the anode is itself the physical location of your oxidation. When we take a look on the other side of this, because a lot of times what we do is we're like, well, oftentimes we have this thing. That's aluminum. I don't want aluminum. I want gold. So gold here is being reduced. And a lot of times we just go ahead and say, you know what, we are using a gold electrode. And then we point and we're like, ta-da, this is my cathode. Notice I have a solid here. So we do in fact need our electrodes to be solid objects so that they can connect to the rest of the equipment. But what we're looking for is we're looking for solids to be our actual physical electrodes, because then we say that the cathode is the site of reduction. Again, that's part of what we all mean in there. That's a physical location for that to take place on. So I'm going to hope that that was enough for how does galvanic cells work with nonmetals needing a surface site. I'm going to hope that's enough information in there. I know some people really like a lot of the engineering that goes into that, and I try to find better pictures of that, but that's where I'm at for right now. Would change in Gibbs standard energy and change in Gibbs energy be used interchangeably with the equation? Potentially determination has it written only as standard. Okay, so let me grab this. Huh. You were correct. So I'll show you why I laughed a little bit. Honestly, I don't doubt you guys. I'm just sometimes like, well, if that's interesting. I wonder if that's true, then there's this other thing I kind of expect to be true and it's not. So basically what made me honestly a little bit startled is the fact that for one equation we have it written out rather obviously when it comes to dealing with E-cell, this notion of here is my standard and here is my standard and there is no standard here and there is no standard here. And both of those are given to you. But then the question is like, hey, I only have this one. What's up with that? So honestly, this is a game where to me, I expect you guys to have this one already kind of under your hat, this one already more or less down, especially because a lot of times dealing without the standard symbol, this equation then becomes more of a conceptual understanding. Because if we're going to do calculations with it, then the version that's given with the standard symbols and saying that my enthalpy and entropy are definitely going to come from tables, basically, this is my calculation version. So this calculation with data tables. So calculation with data tables is the one that's listed on the potentially useful information page. I do understand the question because the question is like, why isn't there any other version of it? And honestly, I think that's just to save us some space, I guess. Because this version of the equation, we usually do this one for concepts. Because usually what we talk about here is basically if I tell you that this is exothermic, and I tell you that this is increasing in entropy, then do you expect this to be spontaneous or non-spontaneous? And so usually we use this version without the standard symbols just to talk about spontaneity and then to do some general assumptions like that. So for the things I put in there, since an exothermic reaction would have a negative value for enthalpy, and then increasing in entropy would be positive, a negative minus temperature times a positive, this whole thing is negative. And so since you expect then your delta G value to be negative no matter what, because both your enthalpy and your entropy essentially are favoring spontaneity, we would expect this to be spontaneous at any temperature. But yeah, I have to admit, I had not paid attention and I had not realized that we only had basically a calculation version of the Gibbs free energy equation where we just had the Gibbs free energy at standard conditions written on the back page. Interesting. I had not realized that. Well, if you do need the conceptual version of the equation, now you know that you will need to be able to think about that on your own. But you might notice that it is the same. It's just this is the one on the right that we use for concepts. The one on the left with the highlighted portions is what we use for calculations. And honestly, that's probably why they're like that. Because we the one without the standard symbol, we don't usually use for calculations. The one with the standard symbol is what we use for calculations. Down here, when we're talking about how to go in between delta G and E cell or delta G standard and E cell standard, those you can go back and forth. And so in that case, keeping track of the fact that the ones that are standard relate to each other and the ones that are not standard relate to each other could be of more value. So had not really thought about the fact that that potentially useful information page is very high on how do we use these for calculations. So the question was actually, are they interchangeable? And this is one of those odd things where the standard really does just give you this idea of standard conditions. So whenever you see the delta G with the standard, that really just is for standard states, which is 1 molar concentrations and 1 atmosphere. And I'm going to put likely 25 degrees Celsius. It doesn't have to be 25 degrees Celsius, but it is likely to be 25 degrees Celsius. And if you don't have a temperature, you get to assume that it's 25 degrees Celsius. So all the little circle means is that you are knowing what the concentrations are. So it is what happens at standard states. So instead of what happens at 0.5 molar or what happens under physiological conditions, none of that. Only for 1 molar, 1 atmosphere is what the standard state means. So it's a very specific set of conditions. So because of that, we usually don't say that delta G standard and delta G are interchangeable because delta G could be for absolutely any combination in any set. And so usually delta G without the standard symbol is for spontaneity of the reaction at any point. Delta G standard is asking, is the reaction spontaneous at standards, under standard conditions, 1 molar, 1 atmosphere. So very specific conditions. The difference between delta G and E cell and the relationship between the two. So essentially, here's my lovely equations. So one of the ways that I like to think about this is when I'm talking about things like E cell or E cell standard, these are in volts. So this is telling me something about the electromotive force, or basically how much force do the electrons have when they go through the wire, which is kind of weird in all honesty. Voltage itself is kind of an odd concept and one we don't deal with a lot in chemistry. Dealing with delta G or delta G standard, these guys are usually trying to talk about work or the potential for work. And we're usually in kilojoules on this side. So you could kind of have an idea of how much force do the electrons have when they go through the wire is related to how much work can I get out of that force. but they're not exactly the same thing, which is why we have these constants to relate them together. Now, that being said, this is the part where when we talk about things in voltage, one of the things that you might notice is we don't take into account in that giant table's over here, all of these, there's different numbers of electrons happening in these reactions. And with the exception of translating things into work, we don't actually care about how many electrons are being transferred. A lot of times we're like, tell me about standard E cell. And the standard E cell value is just dealing with the voltage that's over here in this right-hand column, without trying to do more things with the number of electrons. But if we actually want to talk about work, how much work can I get out of here? Now I actually care about the number of electrons. How many things are actually being transferred? What's actually going on? So they are related to each other, but they are different from each other. F is Faraday's constant. This is basically the charge on a mole of electrons. So I'm not sure that that actually answered what you wanted, but hopefully that helps. I asked lots of conceptual questions. Is it useful to restudy the oxidation and reduction rules that we learned in Gen Chem 1? So I'm going to tentatively say yes, with a question mark, just because I'm not sure what these are. If I had to guess, I'm going to guess that these are the rules for oxidation numbers. I'm going to also guess that this has something to do with like reducing agents, oxidizing agents, because all of that's fair game. You actually do still need oxidation numbers, because if you actually need to figure out how many electrons are transferred, if we give you a brand new reaction, sometimes those oxidation numbers are the things that you need for that. Reducing agents and oxidizing agents don't come up as often, but they are still things we expect you to know. I expect you guys to be able to use that language or be comfortable with that language. So oxidation numbers I actually did a little bit of when we were talking about balancing. So this -2 above my oxygen, this -7 above my manganese, the -2 above the oxygen here, the +4 above the manganese. Those are all oxidation numbers. And again, that's actually what I use to figure out how many electrons are being transferred in this half reaction. So that's where those came from. When I talk about reducing agents and oxidizing agents, there's a couple different things, but one of the main things that we do ask about with oxidizing agents and reducing agents looks a little something like this. Let me go ahead and make this a question. Strongest reducing. I'm going to make, and just give me 2 shakes. Because, you know, I'm going to go back. A shake is an actual unit of time. I have to go back and look if a shake is 2 seconds or if a shake is half a second. It's one of those. Superscript. So these are mostly supposed to be options. Oh no! Those are supposed to be 4 different options. Which of the following is the strongest reducing agent? And you have 4 options. So part of this is going to be a grab your table. And so as I look, oops, that's also supposed to be a solid. So if I look on my table, I can see a gold 3+ with 3 electrons going to gold solid, and I see that with a +1.5 volts and Lower on the table, I can see a silver reaction. And my silver reaction has a voltage of 0.8 volts. So if I want to know what the strongest reducing agent is, I do want the thing that's more likely to be oxidized. I want the thing that is going to be able to provide electrons. So between the two reactions, this reaction, we're just going to circle the whole thing, more likely to be oxidized. So this has the reducing agent. But what you might notice over here is if this is like A, B, C, D, I can't pick both the silver solid and the silver plus as a reducing agent. I have to pick between those two things. So if I want a reducing agent, I need something that allows reduction to happen. I need something that's going to bring electrons to the party. That is, I also need something that can actually be oxidized. That's just silver solid. Silver solid has electrons that it can give up. Silver solid is actually able to provide electrons. If you look in your whole table of reactions, there is no silver 2+ in here. Isn't. That's part of why when I need to grab reactions quickly during an exam review, I have a tendency to grab silver or golds because I know that they are only on here as silver and silver plus and gold plus, gold 3+. So there's no other oxidation states in here for silver and gold. So I can't take away an electron from silver, from the positive silver, from that silver ion. It's not a thing. So the only way I can actually get a version of silver that can act as a reducing agent is to pick this version of silver that is a solid. So that is also one where you do need to know what a reducing agent actually is, and not just how to identify them. But that is something that is much more from Gen Chem 1. So it's much more a Gen Chem 1 style of thing. I thought there was one more in this set. How much material from the previous exam is going to be on exam 4? I don't think as much as there was from exam 2 to exam 3. Whoa. This is one where the main thing I think is going to be two main things: entropy, and knowing what entropy is conceptually. That's going to be on there. We did kind of get to review it, but also the day after the exam, which is tricky. And then the other thing that I think you've actually seen when we look at this potentially useful information page and we're looking at the kinds of equations that are on here, Q shows up in various locations, and K shows up in various locations. So being able to take a reaction, I don't have one right now. I guess we'll just make one. Oh, we'll do an old faithful reaction. H2 as a gas. I'm going to balance this in just a minute. H3 as a gas, and I put a 2 there, and I put a 3 here. If I was going to talk about this reaction either for thermodynamics or I was going to talk about this reaction for electrochemistry, which would be a little weird, but doable, actually, because this is also an electrochemical reaction. This is a redox reaction in here. But we could talk about Q for this reaction, which means I would need to be able to do those products over my reactants and use my exponents, use my coefficients as exponents. So Q is the other piece that is back that we are in fact using for, oopsies, no, that we are in fact using for exam 4. So still using K and Q, but still definitely using expressions of Q. Okay. So it's been about a half an hour. We're at 4 o'clock. Are there any questions in the chat so far?
Yes, ma'am. We got a couple.
Great.
Okay. So, do you know if the SCC or SSC will host an exam review?
Okay.
Could you go over the difference between G and G0 and how to decide spontaneity when you get a value of either one?
Okay.
Could you go over E cell potential and the difference between reduction potential and oxidization potential?
Okay.
Can you go over how to know which direction reaction goes from G values?
Okay.
Could you do a problem where we find K using the E cell potential?
Okay.
And then do we need to know drawing of the galvanic cell? Can you do a cell notation problem, please?
Great. Anything else?
Yeah, that is all I see for now.
Fabulous. Okay. So first of all, that last question was, do we need to know about the drawing of a galvanic cell? Yes. Yes, you do. I don't actually know how many different schematic diagrams done in rectangles that I have made over the years, that I have seen over the years, because they're pretty easy to draw. So we have absolutely drawn those, or asked y'all to draw those. Yeah, drawing of galvanic or voltaic cells is something you need to be familiar with those pictures. Yes. A cell notation problem, I can definitely do one of those. So will the SC host an exam review? I have no idea. That is a valid question. Because I understand more exam reviews are better. I honestly don't know. That is not something that I have in my the thing that I know. So valid question, great question. I don't know the answer. So please do ask them, or ask an SI, ask whoever usually does those reviews. Hopefully they know the answer, because I have to confess up that I don't know. When we're talking about delta G versus delta G standard and spontaneity. So in general, we have a tendency to talk about delta G for spontaneity because this way we can talk about this for essentially any condition. And this is especially useful when we're trying to talk about something like, does an ice cube melt? Because we are trying to talk about going from water as a solid to water as a liquid. And this is something that is temperature dependent. So when it is above 0 degrees Celsius, then it melts. So it's spontaneous. When it is lower than 0 degrees Celsius, then this is non-spontaneous. So we have a tendency to talk about delta G with spontaneous because of the fact that way we can talk about it under lots of different conditions and just, is this happening? Is this not happening? When we talk about delta G standard, the thing is that this no longer now applies to every single condition ever. This is now applying to 1 molar concentrations, 1 atmosphere if it's a pressure, and I'm going to put this again, likely 25 degrees Celsius. So delta G standard, you can still use the word spontaneous. I often try not to. So I often will use this to be like, favors a forward reaction. Just because that way I can differentiate a little bit between what's going on here. But you can still use the word spontaneous to talk about delta G standard, because delta G standard is just talking about, is it spontaneous or non-spontaneous under a very specific set of conditions. So that is what is going on with that one. Now, part of the reason then why we connect delta G standard to K, is because this does allow us then to think about what we expect the magnitude to be. So this being able to connect delta G standard to K is useful to think about the magnitude of K. So essentially, if delta G standard is something like negative 23,000 kilojoules, that is very spontaneous at standard conditions. So I would expect my K value to be very large if that was what I had. I would expect K then to heavily favor products because my delta G standard would be such a large value. So those sorts of things can be useful to get a general idea of how big do you expect K to be based on delta G standard. So that part is useful. Same idea, if my value of delta G standard was something like positive 0.1 kilojoules, then this is non-spontaneous, but it's not very non-spontaneous. So we kind of expect K to be small, K to be less than 1, but not super small. Like, probably 10 to the negative 2, 10 to the negative 3 small, but not 10 to the negative 48. So delta G standard, because it gives us those standard conditions, can tell us, are we expecting K to be big, K to be small, K to be very, very big, K to be either not that small, or K to be very, very small. So delta G standard gives us information about what we might expect K to be. Giant with lots of exponents, big positive numbers, really, really small numbers, general ideas of magnitude. So hope that one helps on delta G and delta G standard. Next up, I answered this question not very well. East area of the cell, oxidation and reduction. So let's go ahead and those are nice right next to each other. So let's go ahead and grab some more reactions. We'll go ahead and grab 10 2 plus nickel as a solid goes to 10 as a solid plus nickel 2 plus, and those are aqueous. And we're just going to say that from this reaction, the question is, what is E cell? So if this is the only question, then you have a couple different options of what to do and how to get there. So one of the things we are going to need to figure out is we are going to need to identify our two reactions in here and what's happening. So here I do have 10 being reduced, and I do have nickel being oxidized. So because that is what's given in the reaction, that's what I need to reflect. So in this case, 10 I had it. They're right next to each other. They're there. So 10, when I grab it off of the table, my standard reduction potential for 10 is negative. I'm going to highlight this thing because I keep losing it. There we go. Negative 14 or negative 0.14. Negative. So that is my standard reduction value that comes off of the table. So this number that I just wrote down is from the table. And I understand that I'm looking at a physical table, so I'm going to go ahead and hop over to my potentially useful information page, and I'm going to find the same thing, which now that I know the number will be a bit easier. So here's my 10. So this is my standard reduction potential. The table says it's a standard reduction potential. So everything in this table are reduction values. The whole table. Everything you pull off of here is a standard reduction value. Now, I also need nickel, and nickel is right below it. So here's the thing. If I pull this off of the table, this is a standard reduction value. So this is negative 0.25. So when I come back over here, and I want to talk about my standard reduction value, the number that I pull off the table for nickel is negative 0.25 volts. But this is for a reaction of nickel being reduced. Nickel is not being reduced. Nickel is being oxidized. So this is the part where in order to actually have an oxidation potential, I have the reverse reaction. So if I actually wanted to talk about what's really happening and what is my standard oxidation potential, then that is the reverse sign of whatever is in the table. The table gives you nothing but reduction values, but one of my reactions is not a reduction. So therefore, one of my values should be the reverse because it is in fact an oxidation value because it's being oxidized. So then if I want to calculate standard E cell, the equation that we give y'all on that potentially useful information states that it's the reduction potential plus the oxidation potential. The reduction potential is right off of the table. The oxidation potential is the one that we solved for and is now positive. And then from there I can solve. Now, positive. The other thing that we can note is because when we were looking at the table, the thing that was reduced is higher on the table. So I should have had an overall positive value for my standard E cell. The thing that is more likely to be reduced was reduced. So therefore, I can go ahead and say that this is a galvanic cell. As a galvanic cell, this should have an overall positive value for E standard, or E cell standard. All that being said, in, I think it's your textbook, it might be Alex as well, has a different thing. And it says the cathode minus the anode. In which case, they mean the reaction happening at the anode minus the voltage of the reaction happening, or the voltage of at the cathode minus the voltage of the reaction happening at the anode. That's what they mean. So in that case, now all I have to do is pull numbers off of the table. That's the real trick here, is if you're using this one, you just pull off the table. So this then is negative 0.14 volts minus negative 0.25 volts, and you get a positive 0.11 volts. Now, that last one certainly looks like it's a lot faster. Keep in mind, we already pulled all the numbers off of the table. I'm not, and I didn't walk through the fact, since I know that the 10 is being reduced, that makes this reaction my cathode. So my negative 0.14 goes as my cathode. Because I know that nickel is being oxidized, that makes this my my oxidation reaction. So this would be at the anode. And because that one's at the anode, that means that my minus sign goes on this side. But those values are both just pulled off of the table. So dealing with E-cell, pick a method and stick with it, because that's going to be the best advice to get you guys on the other side of all of that. So I do apologize that you see both of those, but the best thing I can do is point out that there are, in fact, 2 different ways to solve for that. Sorry about that. I was trained on the flip one of them and add them together version, but this one is an ALEC, so you can't really avoid seeing both of those at this point. So I'm going to come back to the direction of the reaction from delta G, because I think what you guys actually want on that one is a calculation question. Because otherwise this is just, if delta G is less than 0, then it goes forward because it's spontaneous. And if delta G is greater than 0, then you assume it goes backwards because it's non-spontaneous. So that's the super short version of that, but I kind of assume you don't want the short version of that. So I'm just going to kind of put a pin in that one for right now and see what else I can get through. But I may come back and do that one depending on time. I'll definitely do it for the follow-up video. It just kind of depends on what other things I can touch on. The other thing with that question, by the way, and the other reason why I'm actually trying to avoid it unless I have plenty of time, is because I need the big equation for that one. That one involves the Nernst equation. So that involves this guy. So if I was going to do when, not if, when, I do the direction of the reaction from delta G, that one is usually best done by going ahead and doing a full out version of this guy, which has a lot of different variables in it. And we should talk about all those variables and have a reaction that you guys can do Q with and all of that stuff. So it just takes a little bit more time. So I'm going to try to do that in the follow-up video, but I will do it here if I run out of things to do. Find K from E-cell. This is actually the one I wanted to do next because we already found E-cell. So we already did this reaction with tin and nickel, and then it says what is E-cell, and we already found E-cell, and so now all I'm going to do is for the same reaction do you guys have a preferred temperature? Let's do 40 degrees Celsius. Why not? What is K? So I am going to go ahead and I'm going to go grab my potentially useful information sheet, and I'm going to go ahead and grab my equations. And I said plural because they technically are plural. So there is a version of this that then has basically would be at 25 degrees Celsius, which is part of the reason why I'm like, nope, let's just go ahead and do this at 40 degrees Celsius and deal with all the different variables. So the goal is K. There is K. I already have my E cell standard, my positive 0.11 volts. So that can also take a fair amount of time. But we already have that one. And then I have R, T in F, the natural log of K. So in order to solve for this, I have all of these lovely little variables in here. So I have positive 0.11. R is the gas constant. I'm going to go look and find the gas constant on the potentially useful information page to show you that it's here. Where is it? Oh my gosh, there's so many things happening here. Look, there it is. There's R. And it's in joules per mole per Kelvin, but this is the version that we need. So this is 8.314 times T. T is in Kelvin. I gave it to you in Celsius because I'm a big meanie. Plus 40. So there's my temperature. All divided by N. N is the number of electrons transferred. So for N, I'm going to scroll back up and take a look at my reaction. And what I can see in my reaction is everything in my reaction was dealing with 2 electrons. So I basically look out, I just have 2 electrons being transferred over the whole thing. So all I have to do for my number of electrons is 2. The last thing is F. That's also on that potentially useful information page. It's right here. So that is, yeah, 96,485 times 96,485 times the natural log of K. So this is one of the reasons I wanted to do it with the different temperature, is just to showcase the fact that we can go ahead and do this with a whole bunch of different pieces. So I get 0.11 is equal to, I get this top part to be 2600, 3, basically 0.5, divided by 2 times 96,485. But that leaves everything in joules. So then I wind up with 0.11 times the natural log of K. So then I basically get 0.0135 times the natural log of K. So then I can move that over and divide both sides by this 0.01. Then I get 8.15 is equal to the natural log of K. Then to get out of my natural log, I'm going to use E to whatever this was. So this is positive 8. So this is still positive 8 is equal to K. And K is 3,474. When we look back, my value of E standard of the cell was positive. So I should expect this to be a spontaneous cell, something that is going in the forward direction. So that is likely that my value of K should be going towards products, and it is. So, are more product favored. So there is my value of K. Usually the big thing for this is to catch the Celsius. So if your temperature is given, then you need to use it and use all of those bits and pieces. And then don't forget how to get out of the natural log. On most calculators, the natural log and the thing you need to do the inverse of the natural log are usually kind of close to each other, but that's not always true. So being familiar with your calculator is a good thing. Okay. Yeah. So if it was at 25 degrees Celsius, we could have used this guy, which does have a log instead of a natural log, but they should both work. Okay. So, drawing of galvanic voltaic cell notation. Let's do a cell notation problem. So really, on a cell notation problem, we oftentimes ask a really similar question, something like, what is E cell? But now we're going to have cell notation. So I'm going to go ahead and put this like this. And then what else do I want to use? We'll go ahead and use some zinc for funsies. So in my cell notation, you do read this from left to right. So this is actually saying that my magnesium solid is going to magnesium 2+, which would then be plus 2 electrons. So I do in fact read this as my reactants on the left, my products on the right. So therefore I'm also reading this as my zinc 2+, gaining 2 electrons to go to zinc solid. So I do read my cell notation from left to right. If the goal is standard E cell, then again, I'm going to flip back to my big table and find both of these reactions. One of the things I usually encourage people to do is use basically another piece of that scratch paper to go ahead and if my camera for a minute. Basically using it as a straight edge to go across so that as I'm trying to, hold on. As I'm trying to like look at things, I make sure that I can actually go straight across there instead of like accidentally like going down one. So I personally like to use a piece of paper as a straight edge so that I can actually make sure that I'm going straight across there and getting the value that I actually need. So that's one of the tips that I like to do, since you guys are going to be doing this on a piece of paper. The other thing that I personally like to do, which this one I can show off on this screen, because now that I need different things, what did I pick? Zinc. I definitely picked zinc. I love zinc. Also, I'm sorry that my dog is hacking in the background. Magnesium and zinc. He needs to go to the vet to get his allergy shot because he has seasonal allergies. But I have not had time to take him quite yet. So Grant, I've got different colors but I sometimes will use different lines to remind me like what I'm comparing. So what I mean by that is I use highlighters up there, but like I might have just used like straight lines. So now I might use like a squiggly line to be like, here's zinc and here is magnesium. Because that way the squiggle lines tell me that I'm comparing squiggle to squiggle. And earlier when I was highlighting things, I was using tin and nickel. So if I use straight lines here, I'll use squiggly lines down here just to showcase the fact to keep track of what I'm comparing to each other. So in this case, I'm actually showing magnesium is being oxidized and I'm showing zinc is being reduced. So again, the goal is still to talk about my overall standard E cell. I'm going to go ahead and grab these guys and bring them back. Also, I love my dog very much, but one of his many nicknames is Drama Dog. So he will sometimes hack and cough to get attention. Okay, so my magnesium here is being going from solids. Oh, this is being oxidized. That is being oxidized. That's my oxidation reaction. My zinc here is being reduced. Oh, good for me. Did get this to be a spontaneous cell. So anyway, so that does actually match what we'd like this to be is a spontaneous cell. So as far as my E cell, so again, we can have our standard reduction reaction for my negative 0.76 is going to be my reduction. This is also my cathode. My magnesium, on the other hand, I might want my oxidation potential, which would be the flipped sign of whatever is in the table. So if I wanted to add these two together, I can for my standard E cell. But the main thing I'm using here is I'm using the fact that my cell notation is in fact written from left to right. And as it's written from left to right, I do actually read that as reactants and products. So knowing how to read your cell notation is really useful. So that also does mean, so there's my value for my E cell standard. But the fact that these go from left to right does also mean a few things. It does also mean that whatever is furthest here on the left is going to be my anode. It means that whatever is farthest here on the right has to be my cathode. So when I'm talking about my standard cell notation, I can actually look at a glance and I should be able to see solids on those edges, and I should be able to see an anode on one and a cathode on the other. So your cell notation is the time where you do actually see your anode on the left and your cathode on the right. So your cell line notation is a time where you actually do see that. When you're looking at a galvanic cell that is drawn with pictures of beakers, it doesn't have to be that way, especially because beakers, if you moved around the table, would be in the opposite order. Cell line notation is always on a piece of paper, and therefore cell line notation has a left and right. Beakers, because if we were sitting at a table and you're sitting across from me, my left is your right and vice versa. Beakers don't have lefts and rights. Cell line notation has a left and right because everybody who looks at it looks at the page and sees the anode on the left, the cathode on the right, no matter where we're sitting. Okay, it is 4:30, which means it's time to ask for questions again. So are there any new questions in the chat?
There's just one that I see for now.
Okay.
Can we do a problem where we find Q using the Gibbs free energy equations?
Sure.
Okay.
Okay, anything else? I assume no. So just one.
Yeah, no, I don't see any others.
Okay. Okay. Everything is long that's left. So, what do I want? I need the same. So basically, I'm just trying to think about this because I don't have a delta G standard, so I was going to have to make it up. But we'll just go ahead and make up a reaction because that'll work just fine. So we're gonna do 2 of these since that is what everybody wants, or at least what I'm getting from the chat. Okay, so I'm gonna make up a reaction. So since I'm gonna make up a reaction, we are just gonna use aqueous A plus 2B, also aqueous, goes to 3C, also aqueous. We are going to go ahead and be told that for this reaction, delta G standard is equal to negative 5.7 kilojoules per mole. So that is given in the problem. We're also going to go ahead and be told that at a particular time, wherever we are the concentration of A is equal to 0.1. The concentration of B is equal to 0.2, and the concentration of C is 0.01, because it needs to be different. So all of this is given, and the grand question here will be, what is delta G, and does the reaction proceed forward at 25 degrees Celsius? So I'm also going to go ahead and use 25 degrees Celsius to make my life a little bit easier. So I am going to go ahead and use this lovely equation up here. In which case, so this is A, which way does the reaction proceed? So this is not solving for Q. So everything that's in black, even though it's handwritten, is stuff that's given. So I do have a value of delta G standards, and I have a lot of values for Q. But I want to know what the value is of delta G and if my reaction goes forwards or backwards. So what I'm going to do is basically do a little party and be like, all right, I know about delta G standards. Delta G standard is negative 5.7 kilojoules. Then as I go from left to right, this R 8.314 is in joules. So I'm going to have a problem with this comparison in here. There's two different ways to fix it. T is at 25 degrees Celsius, so it's 273.15 plus 25 times the natural log of Q. Q I also need to find. So before I do that, I'm actually going to go ahead and do negative, whoa. To make my units match, I do have two different options. I could go ahead and go from joules to kilojoules, but it doesn't really matter, but I do need them to match. So there's joules and there's joules. So my value of delta G standard, I'm going to go ahead and make that 5,700 to make that match my units. I still need the natural log of Q. So I gave myself everything aqueous. So I do include everything. I need all the pieces. Then this is 3C. So so my Q expression is C cubed divided by the concentration of C times the concentration of A times the concentration of B squared. So all of my coefficients I'm using as exponents for my Q expression. So I can take the amount of C, and that's cubed, divided by my A, divided by B squared. So this is usually one of the big things with dealing with Q, is to remember that we still use exponents. So I'm going to break this down to make sure I don't make mistakes, hopefully. And then 0.2 squared is 0.04 times 0.1, gives me divided by 4 times 10 to the negative 3. So my Q value should still be small. So 1 times 10 to the negative 6 divided by that, and I get something like 2.5 times 10 to the negative 4. So that's my value of Q. Then I'm going to take the natural log of that number. Because this number has a negative exponent, the natural log of Q is also going to be negative. So I have negative 8.294. So that is then the value of the natural log of Q. So that then is something I can put in here. So rewriting everything, 8.314 Now we're in joules. This is 298.15, and the natural log of Q is negative 8.29. So before I do any other math, my delta G standard gave a negative number. My natural log of Q also gave a negative number. So when I put all of this together, I should expect this to basically already be still spontaneous, but even more so than what I started with. So if the only question I actually needed to answer if the only thing I need to answer is, does the reaction proceed forward? I know this answer already because I have a negative number and it's going to get more negative. So this is yes, this does proceed forward. Is no one giving attention to you? You poor thing. Should you come back to hack at me? Yeah, I know. So I already know that the reaction does in fact proceed forward without doing any calculations because I started with it. Well, we did some calculations, right? We took the natural log of Q. That's how I'm making this assumption. I have a negative value for delta G standard and my natural log is negative. So all I'm going to do is make this even more negative. Therefore, I know the reaction proceeds forward because my value of delta G, just delta G, is going to be negative. Continuing with the math. Times 298.15 times 8.314. So negative 5,700 plus a negative 20,500. Yep, that looks good. So a final answer for my value of delta G is 26,259. That is in joules. So we could also change this to perhaps the more reasonable negative 26.3 kilojoules is equal to my value of delta G. So we can look at values of delta G. And again, because that's a negative value, we expect that reaction to still go forward. And we make that decision because my value of delta G is negative. So even if my value of delta G was negative 4,000, as long as delta G is negative, you assume that the reaction is spontaneous and it goes forward. So we don't actually have to compare delta G to delta G standard to make that assumption. As long as delta G is negative, the reaction is spontaneous, the reaction goes forward. Okay, let's go ahead. Okay, so now I did that one. This other one is finding Q from delta G or drawing a galvanic cell. Let's go ahead and do Q from delta G. Let's go ahead and do some thermodynamics in here. So we're going to do a different reaction just for fun. And what we're going to do is we're going to say that we're just going to go in between these two different numbers or two different letters. So if we go in between like 2D aqueous is in equilibrium just with E aqueous. And we'll go ahead and give a value of delta G as being negative 2.2 kilojoules, the value of delta G standard as being negative 4.1 kilojoules, and the question's going to be, what is the value of Q? So the other thing I would say is, for those of y'all that would like to do more calculation practice, you guys can essentially challenge each other and make up your own questions. You guys have been taking general chemistry now for a while, so you guys could try to write your own questions at this point. If you make them so you can't solve them, come in and talk to one of us, and we'll help set you straight or help be like, I think you were missing information in here. In this case, because there's no temperature given, you can either say, oh no, I forgot the temperature, or you can come back and say like, well, we'll just go ahead and assume 25 degrees Celsius. So if there's no temperature given, then yes, you do get to assume you're at 25 degrees Celsius. So for this one, somewhat similar. So I did just go ahead and give values of delta G and delta G standard. You could also have this where we could have made you guys solve for delta G standard. So there's two different ways to solve for delta G standards. Either you guys can have a table of data and we can give you like values of delta H and values of S standards, and then we can make you guys solve for delta G standards by plugging in. So actually, I know I have this value over here, but if we were to do that, it could look something like this. So here's E and here's D, and here's a value of delta H of 7.1, and here's a value of delta S of 110, and here's a value of D of, I'm getting tired, 6.9, and value of S of 78. And since I have a reaction that is 2 Ds in equilibrium with E, then what I could have done, which maybe we'll just go from here, S is going to be in joules per Kelvin per mole. Enthalpy is going to be in kilojoules. What we then have to do is we then have to go ahead and do products minus reactants. So therefore, I can solve for my enthalpy by taking my value of E and subtracting 2 times my reactants. 7.1 minus 2 times 6.9, negative 6.7 kilojoules. And then I can go ahead and solve for my value of delta S. This is technically a standard states. Same general idea. 110 minus 2 times 78, value of delta S. Negative 46. We're still assuming 25 degrees Celsius. So then I could come down here and solve for my standard delta G of negative 6.7 kilojoules minus my temperature, 298.15. So I'm using delta H minus T delta S, technically all the ones with the standards, and delta S of negative 0.046, because that one is in joules. And then my value of delta G standard could go into my equation. So there are different ways to put this together. Get negative 6.7 minus, which means plus 13.7. So I get a positive 7.01 kilojoules for delta G standard. So lots of different ways to set up the reaction. So again, I was trying to do a quick way and say, hey, let's just plug and chug some numbers. But instead of giving you guys delta G standard, we could ask you to solve for delta G standard. We actually hadn't done one of those before, so since I know I'm running a little bit short on time, I wanted to do one of those for example. But we will just go ahead and assume that it looks like this. Yeah. But we're going to go ahead and use everything in blue. So in this case, I just get to go ahead and plug everything in. Negative 2.2 is equal to negative 4.1. Those are all in kilojoules. My gas constant is not in kilojoules, that's in joules, times the gas times the temperature, 298.15, times the natural log of Q. So then doing all of this over here, negative 2.2 plus 4.1. This gets me positive. So I'm adding 4.1 to both sides to get this positive 1.9. At this point, I'm going to go ahead and change my units. When you do that is up to you. But this is really 1,900 is equal to 8.314 times 298.15. 2,478.8 times the natural log of Q. So now I get to divide both sides by 2,478.8. 78.8. God, my handwriting is getting bad. Sorry about that. So I get 0.766 is equal to the natural log of Q. This is a positive number still, so E is going to be the positive 0.766 is equal to Q. No. There. I get Q of being 2.15. And this is one where if we had more information, we could in fact keep going. So this was supposed to be for this particular reaction. So that is supposed to be for the concentration of E divided by the concentration of D squared. So then if we were told that E is 1, if the concentration of E equals 1 molar, what is D? We could keep going, right? So this is always the hard thing with some of these problems is when I have to make something up off the top of my head, I never quite know how complicated to make it. So again, you can just so you can imagine what other combinations if we wanted to take things further. So this can be as straightforward as here's a bunch of numbers, plug some things in. This could be here are some numbers, here are some more numbers, figure out what delta G standard is before you get going, and then plug in. Or this could be, here are some numbers, plug everything in. Oh, but we'd actually like you to solve for a final concentration, not just for Q. So any of the equations that have to deal with Q, I a lot of times think of them as like accordion questions. I don't know if you've ever seen they stretch, they have this interesting ability to either stretch out where you can make them way more complicated or much longer than original, or you can also shrink them down. Because if the only thing we actually needed to do was solve for Q, given this information, that was actually just this information that was here, and then that was my Q value of 2.15. So the hard thing with dealing, and so I understand very much the question of trying to deal with this equation, because sometimes this is plug and chug. Here's delta G, here's delta G standard, solve for Q, go. In which case you can do that. Other times you need something in Q, so that's where I kind of kept going in red in case you wanted to keep going that way. Or we could have been jerks, and instead of giving you delta G standard, we could have given you a little data table and asked you to solve for delta G standard. So the ones that involve Q are problems that can naturally be longer than others. It just kind of depends on the setup. Other questions from the chat right now?
I think just one more.
Okay.
Can you do a problem where we change the temperature for a delta G standard problem? So we have to use enthalpy and entropy.
Sure. Okay, so did that one. So since I already made a table of data, and we already did one calculation of delta G standard, I'm gonna go do that one because I already kind of halfway made that question. And honestly, making up all the numbers is half of the work. So here, so what I am going to go ahead and do is I'm going to go ahead and take my lovely table of data. We'll go ahead and do it all again. So this is the kind of problem. So we solved this one already once, dealing with just 25 degrees Celsius. But in this case, all we're really going to do is we are going to now assume that for my delta G, actually, no, I'm going to make this better. So given this table of data, calculate K at 30 degrees Celsius. Given that. So at first glance, it looks like it doesn't match, but this is where essentially what we need to do is we need to calculate delta G at 30 degrees Celsius using my standard enthalpy value minus T delta S. And then once we have delta G, we're going to plug it in and solve for K. So since I made this longer, and we are going to still assume that this is, what did I say this was? E and D, so this is 2D going to E. So essentially what I need to do is I need to solve for my value of delta H. So that is still my, so delta H is still 7.1 minus 2 times 6.9, just like it was before, which got me negative 6.7 kilojoules for delta H. I'm going to come down here, negative 6.7 kilojoules minus my T now is 273.15 plus 30 times S. S is going to be products minus reactants, 110 minus 2 times 78. So 110 minus 2 times 78. I still get that negative 46, but that is in joules. So when I come down here, that is 0.046. So now I do want to go ahead and solve for my value of delta G standard, but I'm at a different temperature, 273.15 plus 30. So this is actually at 303.15. So negative 6. We're just going to go to 6,700 minus that we said is 303 times 0.046 times negative. So this is going to be negative 13.94. Sorry, I'm laughing because even though the entropy is not favorable, this is, oh, no, I did it both ways. Oh, no, oh, no, oh, no. Sorry, this is kilojoules and this is kilojoules, so I can't do both of those. Sorry, 6.7. This is kilojoules and this is kilojoules. The units have to match. The units have to match. So my delta G standards, don't change them both. Is 7.24 positive kilojoules. Then I said we were going to go ahead and go to K, because apparently I thought we should just do more calculations for funsies. So where is delta G in K? Here's K and delta G standard. Had to be in there somewhere. So I have a value of delta G. This is in kilojoules. Now I am going to move this to joules, because my 8.314 is in joules. My temperature is still at that 303.15, and I've got the natural log of K. I have a negative sign in there that I am not going to lose. So this is then divided by 8.314, divided by 303.15, and there's a -1 thrown in there. So I wind up with something like negative 2.87 is equal to the natural log of K. So this is e to the negative 2.87 is equal to K. This is a negative number. K should be small. Also, we had a positive value of delta G standard, so K should be small. K is 0.056. So what you can hopefully see in there is, with my value of delta G standard being positive, basically 7 kilojoules, I have a value of K that's less than 1, but it's not that far less than 1. So delta G standard and K deal with magnitude. Delta G standard should tell you roughly the magnitude of K. So the fact that I was in basically the single digits when we were in kilojoules, but positive, gives me this value that is close-ish to 1, but not 1, smaller than 1, but not times 10 to the negative like 34. Like, it's not that small, but it's small. It's non-spontaneous. Reactant favored. It's reactant favored. Okay, it is 5:01. Are there any other questions in the chat?
No, ma'am, you got them all.
All right, fabulous. So I think I still didn't do one of these, which was about drawing a galvanic cell. I did mention the fact that, yes, you do need to do that. And we do have those videos up in the 701 section. I will be making a follow-up video because there were questions that my class asked that I did not get to. They're somewhere hiding over here in the really, really small font, but there were still a couple of ones I didn't get to do, so I'll make a short follow-up video. And Dr. Diekman still has his exam review that he posted information for in the 701 section. So everybody, good luck. Exam is on Saturday at 10 a.m. Don't forget. Have a good night. Bye.